Welcome to the Radiographics Podcast. I'm Wendy Gibbs. This week we're excited to have two new voices on the podcast, Doctors Shahryar Faghani and Mana Moassefi, who are both postdoctoral research fellows at the Mayo Clinic. They're experts in artificial intelligence and will be discussing the recently published paper about AI for breast imaging.
New Horizons: Artificial Intelligence for Digital Breast Tomosynthesis. Artificial intelligence, which is an attempt to simulate human intelligence, defined as the ability to automate decision-making processes. By definition, AI in general includes many technologies, which some of them are as simple as the first computer-aided detection tool that was approved by the FDA in 1998, or even our daily calculators. However, most of the time, when people refer to AI, they mean a subset of AI, which is called machine learning. Machine learning is defined as the ability of machines to identify patterns and automatically learn from data for the purpose of predicting unseen or future data. Recent years have seen a rise in deep learning as a machine learning subfield due to its ability to perform automated feature extraction from data, ease of training, and superior performance over other conventional machine learning algorithms. Convolutional neural networks are the mainstay of deep learning models, where they extract abstract features from adjacent pixels through convolutional operations.
Digital breast tomosynthesis, or DBT for short, has become widely accepted for breast cancer screening, allowing multidimensional cross-sectional imaging of the breast, owing to the acquisition of multiple projection images at different angles, which are then reconstructed into image sections. DBT has numerous benefits compared with conventional full-field digital mammography, including decreased confounding overlapping tissue and visual accentuation of imaging findings. In addition, DBT has been shown to significantly increase cancer detection rates by 1.2 to 2.7 per 1,000 cases and decrease false positive rates. The use of DBT has increased dramatically in the United States since its first FDA approval in 2011. As of March 2022, 82% of all breast imaging facilities in the United States offer DBT. However, its growth has started to plateau in recent years. Barriers to the wider clinical use of DBT include increased equipmental costs compared with those of digital mammography units, larger digital storage requirements, longer interpretation times, and concerns about the quality of the images. So the benefits of using DBT are more accurate overall and less likely to result in false positives, much greater accuracy when screening for breast cancer in people with dense breasts, earlier detection of breast cancers in people with breast cancer symptoms. But as I said, there are limits. Here and now we want to discuss this article that reviews potential applications of AI for addressing a few of DBT application limits. The first commercially available mammographic AI-based tool approved by the FDA in 1998. It was aimed at detecting suspicious findings to increase radiologist sensitivity for cancer detection. That model had its own issues more than its benefits. As time passed and the technology world evolved, the use of AI in medicine also evolved. Today we have better data, better computational resources to work on that data, and more complicated and sophisticated models and algorithms that can think more like a human being. With this in mind, here is a list of recent AI applications for DBT described in the literature. 1. Non-inferior or improved sensitivity and accuracy for cancer detection. 2. Decreased workload. 3. Decreased recall rates. 4. Localization and classification of abnormal imaging findings. 5. Increased conspicuity of suspicious lesions. 6. Reduced radiation dose. 7. Breast cancer risk assessment. 8. Improved quality of DBT image acquisition. 9. Visual reconstruction of the non-compressed breast for post-surgical planning. 10. Geographic evaluation of patient access to DBT. We will talk about a few of these applications as we go forward and explain the studies which use the AI.
A common focus of AI tools on DBT is cancer detection, the foundational purpose of screening mammography. While most current AI applications are designed for DM rather than DBT, there are multiple potential opportunities to use AI in DBT breast imaging. However, there are a few challenges with applying AI in DBT. First, the datasets used for DBT algorithm development are much larger in terms of memory requirement than those used for DM algorithm. This is due to the larger digital size and a larger number of acquired images in DBT examinations, and thus the larger computational capacity required. Second, the quality of AI models is often dependent on the quality of the annotations. The annotations in DBT examinations are more complicated than those in DM. The pixel-level annotations that are often necessary to train AI algorithm for the identification of suspicious finding require annotations on multiple sections for DBT as opposed to the one or two images required for DM. Furthermore, DBT image annotation is more challenging because the spatial resolution of tomosynthesis sections is lower than that of the DM images. Therefore, this process is more time-consuming for the radiologist performing the annotations and more technically intensive. The third challenge is the smaller number of de-identified publicly available training datasets for DBT rather than the ones available for DM. Fourth, there is a greater variability in breast tissue appearance across different DBT vendors compared with DM vendors, which limits the model's generalizability. Each of these technical factors reflects a newly recognized challenge as the use of AI in DBT applications continues to expand. Before jumping into AI developments for DBT, first, let's talk about different AI tasks. AI tasks in general could be categorized into three main categories: classification, localization, and image generation. Let's start with the classification. Classification is assigning a class label to an input image that falls into three categories. The first one is binary classification. For example, to predict the presence or absence of breast tumor. The next one is multi-class classification. For instance, distinguishing different BI-RADS grade. And the last one is multi-label classification. For example, looking for the presence or absence of calcification and the presence or absence of architectural distortion at the same time. The next category is localization, which in DBT essentially equals to abnormality recognition, either by semantically segmenting the abnormalities such as calcifications and architectural distortions by drawing a fine line around them, or detecting the suspicious lesions and drawing a bounding box around them. And last but not least, image generation, which is synthesizing images that do not exist. For example, generating high-resolution images from low-resolution images or generating full-field digital mammography from DBT images. Now, let's review the recent AI developments in DBT. I will start with the classification. Numerous research studies have demonstrated that the use of AI algorithms result in non-inferior or improved sensitivity for cancer detection compared with the sensitivity of traditional methods. In one study, Pinto et al. Showed that using a single-view DBT and AI setup could allow for a more effective screening program with higher performance, especially in terms of an increase in cancer detection rate than using single-view DBT alone. Now, let's talk a little bit about localization tasks. As mentioned before, one common strategy for lesion localization is to train a CNN model to create bounding boxes around suspicious imaging findings, whereby each bounding box may be associated with different confidence level for malignancy. For instance, a group of researchers developed a unique approach to localizing malignancy, training a deep learning algorithm on normal DBT studies and thereafter automatically creating visual projections of what normal tissue would look like in each study. The system concluded that there would be a higher likelihood of malignancy where it couldn't definitely predict the appearance of assumed normal tissue. Here are some examples for the generative tasks. The first one is increased conspicuity of suspicious lesions. One use of post-processing AI reconstruction techniques is to enhance the conspicuity of malignancies in DBT sections. In an attempt to increase the conspicuity of suspicious lesions, investigators have targeted the synthetic two-dimensional mammography, or STM for short, of the DBT sections themselves. In computer-aided based approaches, suspicious regions are identified on DBT sections and then projected onto a two-dimensional domain to render an SDM image with increased depictability of suspicious lesions. Fotin et al. Tested an enhanced SDM image in a 5-reader study of 30 cases, which achieved a decrease in radiologist interpretation time and increase in sensitivity and specificity. The next example of the generative task would be reduced radiation dose. Combination DBT examination, which include both DM images and tomosynthesis volumes, involve approximately 2 times as much radiation as DM alone. In order to reduce the radiation dose of DBT to that of DM, an SDM image was developed to replace the DM image. According to most studies comparing DBT plus DM with DBT plus SDM, false positive rates and cancer detection rates are similar. As discussed earlier, AI has been used to develop SDM images that mimic DM images or enhance the appearance of suspicious findings. In addition, some studies tried to reduce the radiation dose of tomosynthesis volume. AI models have been used to reduce noise, lower radiation doses, and improve image quality. For example, Leo et al. Trained a deep learning model to generate full radiation dose DBT images from half those images. Visually, the conspicuity of microcalcifications, breast tissue, and vascular structures on the generated full dose images was identical to that on the true full dose images. The authors concluded that this is a promising technology for future dose reduction.
As we previously mentioned, the use of AI support tools as compared with independent radiologist evaluation may also have the potential to decrease reader interpretation times, while demonstrating equivalent to superior performance metrics. Van Wickel et al. Found that the amount of time that a radiologist spent reading DBT studies decreased from 41 seconds to 36 seconds with the use of AI, resulting in 12% decrease in reading time. More strikingly, Conant et al. Found a 53% decrease in reading time for the average radiologist, with the reading time decreasing from 64 seconds with independent reader to 30 seconds with the use of AI. The authors suggested that this drastic decrease in reading time may be related to the availability of AI analysis, including identification of suspicious imaging findings and confidence score labeling, upon opening the DBT study rather than the end when CAD has traditionally been used. Using multiple modalities for training an AI model is another point worth mentioning here. In one study, a prototype linking DBT and automated breast ultrasonography was developed and applied prospectively to 101 diagnostic examinations. This prototype demonstrated a sensitivity of 97% for malignancy detection across these modalities, demonstrating a capability to aid in the automated localization of suspicious DBT findings with sonographic support. In conclusion, recent research indicates the existence of various potential AI applications within the DBT imaging value chain. These applications range from the identification of abnormal breast imaging findings to workflow improvements and patient safety considerations. Use of AI has been shown to improve radiologists' cancer detection rates, reduce recall rates, and reduce reading times for DBT. Multiple research studies have shown the non-inferior diagnostic capabilities of AI tools as compared with radiologists for the identification and characterization of abnormal DBT findings. The majority of these applications are still in the research stage, while there are already several FDA-approved AI products for the clinical workplace. Finally, we need to say that at each step of the breast imaging process, from the decision to perform a screening and image acquisition to the reporting of image findings and follow-up recommendations, there are multiple potential opportunities for AI to augment the benefits of DBT. By reviewing this paper, you can find more details about the opportunities and challenges of AI in DBT.
Fantastic. That was fascinating. And thank you for that. All right, that's it for this week's podcast. Join us again in 2 weeks for more summaries.